Section 1 Introduction 1. Introduction. In recent years, we've observed a rising trend towards scaling neural networks. This scaling primarily increases the depth, or the number of layers, for enhanced expressivity, leading to the creation of many powerful deep networks. Additionally, strategies such as the sparse mixture of experts, MO, models and model parallelism approaches have been employed to effectively enlarge the hidden dimension of the network. Next on the list to scale is the sequence length, which we believe is beneficial to be unlimited. Overcoming the limitation of sequence length has several key advantages. First, it offers the model a larger memory and receptive field, which makes it more practical for interacting with humans in the world. Second, a longer sequence or context includes more complex causal links and paths for reasoning that the model can make use of during training. Conversely, shorter dependencies often contain more deceptive correlations that can hinder generalization. Third, it helps to explore the limits of in-context learning, which could revolutionize many-shot learning. An exceptionally long context may help the models mitigate the problem of catastrophic forgetting. The primary challenge in increasing sequence length is finding the right balance between computational complexity and the expressivity of the model. RNN-style models have been the main choice for increasing sequence length. However, their sequential nature restricts the possibility of parallelizing training, which is vital for long sequence modeling. More recently, state space models have attracted attention for sequence modeling. These models can function like a CNN during training and transform into an efficient RNN during testing. Despite performing well on long-range benchmarks, their performance on regular lengths doesn't match that of transformers, mainly due to the limits of model expressivity. Another approach to increase the sequence length involves reducing the complexity of transformers, particularly the quadratic complexity of self-attention. Techniques like implementing sliding windows or convolution modules over the attention could make the complexity nearly linear. However, this compromises the ability to recall early tokens, causing the model to forget the prompts at the start of the sequence. Sparse attention, which reduces computation by making the attention matrix sparser, retains the potential to recall information from far back in the sequence. For instance, sparse attention can achieve O(n)(sqrt(n)(d) time complexity with a fixed sparse pattern. Beyond these fixed patterns, learnable patterns have also proven useful for sparse attention. We also see other efficient transformer-based variants, including attention, kernel-based methods, downsampling approaches, recurrent models, and retrieval-based methods. However, none of these have scaled up to 1 billion tokens yet. In our work, we successfully increased the sequence length to 1 billion tokens. Our solution, called LongNet, replaces the attention component of standard transformers with a new element called dilated attention. The fundamental principle here is that the attention allocated decreases exponentially as the distance between tokens increases. We demonstrate that it achieves linear computational complexity and a logarithmic dependency between tokens. This resolves the conflict between the limited resources for attention and the need for access to all tokens. In practice, LongNet can be converted into a dense transformer, which smoothly integrates with existing optimization techniques for transformers, like kernel fusion, quantization, and distributed training. Thanks to its linear complexity, LongNet can parallelize the training across nodes, breaking both computational and memory constraints with a distributed algorithm. This enables us to efficiently scale up the sequence length to 1 billion tokens with almost constant runtime, whereas a traditional transformer would suffer from quadratic complexity. Section summary. In recent years, there has been a trend towards scaling neural networks, particularly in terms of depth and hidden dimension. However, increasing the sequence length, which is the last atomic dimension of the network, introduces significant advantages such as larger memory and receptive field, more complex causality and reasoning paths, and the potential for in-context learning. The challenge lies in finding the right balance between computational complexity and model expressivity. Different approaches, such as RNN-style models, state space models, and sparse attention, have been explored, but none have been scaled to 1 billion tokens. In this work, we propose LongNet, which replaces the attention component of vanilla transformers with dilated attention, achieving linear computation complexity and logarithmic dependency between tokens. This allows for efficient parallelization and scaling up to 1 billion tokens. Section 2 LongNet. Let's delve into our proposed method, LongNet. It's grounded in the core concepts of transformers and their self-attention mechanism. Essentially, self-attention is a process that maps a query, along with a set of keys and values, to an output. In simple terms, we can imagine this as the method being given inputs labeled as Q, K, and V, which are matrices, and it works out an output, O. However, there's a challenge when dealing with long sequences. Self-attention has a problem because its effectiveness decreases as the sequence length increases. This is due to the fact that every single query would have to refer to all keys and values, which leads to an inefficient process. Sparse attention is one way to work around this problem. It's a modification of self-attention that limits the query's reach to only a subset of keys and values, thereby saving computational resources. How does sparse attention do this? It introduces something called a sparse attention pattern, represented as a matrix S, which determines which specific keys and values that the query Q can refer to. An example of this can be seen in sparse transformers where the pattern is divided into two parts, a local pattern and a strided pattern. The sequence is split into blocks of a certain length. The local pattern allows a query to refer to tokens within the same block, while the strided pattern allows a query to refer to the last few tokens of each block. The local pattern and the strided pattern are represented mathematically by specific conditions on indices which determine which elements in the sequence the query can attend to. This brings us to a crucial part of our method, dilated attention. To visualize this, imagine dividing the input, Q, K, V, into equal segments with a length of W. Each segment is then made sparse along the sequence dimension by choosing the rows with a specific interval R. The sparsified segments are fed into the attention mechanism in parallel, after which they're scattered and concatenated to create the output O. Interestingly, in practice, this dilated attention can be transformed into dense attention between a gathering operation over the input, Q, K, V, and a scattering operation over the output. This means it can make direct use of any optimization for regular attention, like flash attention. Dilated attention can substantially reduce the computation cost by a certain factor over regular attention. The segment size W and the dilation size R have their own trade-offs. Increasing segment size can improve efficiency but reduce the globality of attention, while increasing dilation size reduces the computation cost by approximating the attention matrix. To capture both long-range and short-range information efficiently, we use a combination of dilated attentions with different segment sizes and dilation rates. Note that the computations for these different dilated attentions are done in parallel because there is no dependency among them. Through our experiments, we found that dynamically calculated weights work better than fixed ones. For a query that refers to keys in different dilated attentions, our method to mix these dilated attentions is comparable to gathering keys from different segments and calculating their softmax together. The local attention should be precisely computed, while the global attention can be approximate. Therefore, we usually set a larger segment size with a larger dilation size. Moreover, we gradually increase the segment size for each attention until it reaches the maximum length or the number of attention patterns. In practice, we usually set the segment and dilation sizes to follow geometric sequences for an exponential attention field. This allows us to efficiently handle long sequences with our proposed method, LongNet. Section Summary. LongNet introduces dilated attention as a solution to the computational inefficiencies of self-attention in transformers when dealing with long sequences. Dilated attention splits the input into segments and sparsifies them along the sequence dimension, reducing the computation cost significantly. By implementing a mixture of dilated attentions with different segment sizes and dilation rates, LongNet efficiently captures both long-range and short-range information. Section 2.3 Multi-head dilated attention. The section you've provided discusses a variant of attention mechanisms known as multi-head dilated attention, and its computational complexity and token dependencies. In this mechanism, we make use of multiple heads, and each head performs its computations a bit differently from the others by dealing with various parts of the query key-value pairs. To explain this further, let's imagine we're dealing with the JTH head. We assign an offset value, denoted by S_j, equal to the remainder of j divided by r. Here, R represents our rate of dilation or the step size for sampling. Then, for this JTH head, we select different parts of the query, Q, key, K, and value, V, pairs, which we call Q tilde, K tilde, and V tilde. This selection is done in steps of R, starting from the offset S_j, and up to the next value of I, for Q, K, and V separately. After processing all heads, we combine their outputs, akin to standard multi-head attention mechanisms. The next part of the section deals with the computational complexity and token dependency. Here, we use dilated attention with a segment size and dilation rate denoted as R and W. For each query key-value pair, we transform it from a size of nxd, using real number notation, to a size of with rxd. As a result, the computation of the attention mechanism can be quantified as two nude R² operations, also known as flops, floating point operations. We can extend this notion to consider dilated attention with multiple segment sizes and dilation rates. In this case, The flops can be given as second times the sum of w underscore I, r underscore I squared over I, ranging from 1 to k. Assuming certain conditions for segment sizes and dilation rates, we can estimate the flops using a constant w underscore 0 and a common ratio alpha, for geometric sequences w and r, as given in the formula 2 asterisk alpha, alpha 1, w underscore o asterisk nd. This indicates that the computational complexity of dilated attention is approximately proportional to the product of n and d. The paper then explains that the information of each token can be propagated to a maximum distance of d, and gives the formula for calculating d further. It establishes that the maximum path length of a sequence with n tokens can be estimated by a logarithmic formula. This provides a proof that the token dependency is approximately proportional to the logarithm of n, which is highly beneficial for computational efficiency. Section summary. In the multi-head dilated attention, different heads compute different parts of the query key value pairs by selecting offsets. The outputs of the heads are then concatenated to form the final output. The computational complexity of dilated attention is approximately O, nd, and the token dependency is approximately O, log n, allowing information to be propagated to a maximum distance of d. Section 3. LongNet as a distributed trainer, scaling up to 1B tokens. We're now going to discuss how LongNet can be used as a distributed trainer to handle a staggering 1 billion tokens. Even though the computational complexity of dilated attention has been dramatically decreased to an order that is directly proportional to the product of sequence length and number of attention heads, it's still impractical to expand the sequence length to millions on a single GPU because of computational and memory constraints. Several distributed training strategies for large-scale model training have been proposed, including model parallelism, sequence parallelism, and pipeline parallelism. However, these methods prove inadequate for LongNet when the sequence dimension is extremely large. Now, let's dive into the distributed algorithm we've adopted. We exploit LongNet's linear computation complexity to distribute training across the sequence dimension. Our explanation here assumes that we're working with 2 GPUs, but the same approach can be applied to an arbitrary number of devices. First, we divide the input sequence along the sequence dimension, assigning each subsequence to a separate device. Then, we transform these sequences into queries, keys, and values on their respective devices. For segments of a sequence that are shorter than or equal to the length of the sequence on the local device, we compute the attention locally. If the segment length is greater than the local sequence length, the keys and values are spread across different devices. As a result, we need to gather these key value pairs before we can calculate the attention. To perform this gathering operation, we transform the queries, keys, and values into a simplified form. Then we implement an all-gather operation to collect these key value pairs. Notably, during the backward computation, this all-gather operation transforms into a reduce-scatter operation. Here's an important difference from traditional attention. The sizes of these simplified keys and values don't depend on the sequence length, which means the communication cost stays constant. Finally, we calculate the cross-attention using the local queries and the global key value pairs. After computing these output values on each device, we then concatenate these results to obtain the final attention output. This distributed algorithm is complementary to other parallelism strategies, including data parallelism that divides the batch dimension, model parallelism that splits the hidden dimension, and pipeline parallelism that partitions the layers. Section summary. The section discusses the challenges of scaling up the sequence length in LongNet due to computation and memory constraints on a single GPU device. To address this, a distributed training algorithm is proposed, which splits the input sequence across multiple devices and computes attention locally for shorter segments, while collecting and sparsifying key value pairs for longer segments. The algorithm allows for efficient communication and computation across devices, enabling the training of LongNet on sequences of arbitrary length. Section 3.2 Scaling up to 1B tokens. In Section 3.2, we discuss the potential of scaling up to a whopping 1 billion tokens, something made possible thanks to advancements in distributed systems. The process begins with a sequence length of 8,000 tokens, and we gradually increase this length until we reach the maximum memory capacity of the GPU. In order to maintain a steady 1 billion tokens per batch, we adjust the batch size accordingly. We design each model to accommodate different sequence lengths, featuring up to 3 segment lengths. These lengths include 2048 tokens, the number of tokens allocated per device, and the total sequence length. To get a clear understanding of performance, we calculate the average speed of forward propagation across 10 different runs. We then turn our attention to comparing the performance of 2 types of attention mechanisms, vanilla attention and our custom-designed dilated attention. Both these mechanisms are implemented using the Flash attention kernel, chosen for its memory-saving and speed-enhancing qualities. Our findings demonstrate that dilated attention is remarkably effective in scaling up the sequence length while maintaining almost constant latency. By breaking down the sequence dimension, this type of attention mechanism can tap into the power of distributed systems, thereby increasing the sequence length to as many as 1 billion tokens. On the other hand, vanilla attention doesn't fare quite as well. It's hampered by a quadratic dependency on the sequence length, meaning that latency dramatically increases as the sequence length grows. In addition, vanilla attention lacks a distributed algorithm that can overcome limitations related to sequence length. These observations underscore the benefits of our approach, which has linear complexity and employs a distributed algorithm, crucial components of LongNet. Shifting to section 4.1, we delve into the setup. We implement LongNet in language modeling. For the core architecture, we employ Magneto, which uses XPOS relative position encoding, but with one key difference. We swap out standard attention for our custom-designed dilated attention. The base configuration of Magneto, which we use, includes a hidden dimension of 768, 12 attention heads, and 12 decoder layers. To pre-train the model, we use the stack dataset, a vast collection of source code spanning over 300 programming languages. We preprocess the data using the TikToken tokenizer 1 with CL100K_base encoding. The training process consists of 300,000 steps, with each batch containing 0.5 million tokens. More details about the hyperparameters are available in the appendix. All the experiments have been conducted based on the codebase. Section summary. The authors demonstrate the feasibility of scaling up to 1 billion tokens using distributed systems. They compare the performance of dilated attention and vanilla attention, showing that dilated attention can scale the sequence length with constant latency, while vanilla attention suffers from quadratic dependency and increased latency. They implement LongNet on language modeling using Magneto with XPOS relative position encoding and pre-train the model with the stack dataset. Section 4.2 Results. In Section 4.2, we report on our results comparing our proposed model, LongNet, with standard and sparse transformers. All these models differ primarily in their attention layers, but are otherwise the same. We tested these models across varying sequence lengths, from 2000 to 32,000, adjusting the batch size to maintain a constant number of tokens per batch. For LongNet, we set segment lengths between 2048 and 32,768, with a variety of dilation ratios from 1 to 12. Our sparse attention models were configured in a fixed pattern, with multiple heads focusing on different subblocks. The size of each block was set to 2048. To ensure fair comparison, we adjusted the sparse ratios of these models to match the computational complexity of LongNet. Vanilla transformers, on the other hand, have fully connected, dense attention layers, which leads to higher computational cost. Because of these computational limits, we only scaled these models up to a sequence length of 32,000. All our models were implemented based on Flash Attention 2 to optimize training efficiency. We developed specialized Flash attention kernels for both sparse and dilated attention. Our models were tested on the stack dataset, with model performance evaluated using the perplexity metric across a range of sequence lengths from 2000 to 32,000. For input sequences longer than the model's maximum length, we used blockwise causal attention, BCA, a leading extrapolation technique for language model inference. We also removed absolute position encoding. The results highlighted several key insights. First, increasing sequence length during training generally improves the language model. Second, extrapolation doesn't work well when the sequence length far exceeds what the model was trained on. And lastly, LongNet consistently outperformed baseline models, underscoring its effectiveness in language modeling. In Section 4.3, we examined how sequence length affects the performance of language models. Prior work has shown that increasing model parameters or training tokens affects how well language models perform. We wanted to see if similar effects occur when we increase the context length during training. We tested our models with input sequences of varying lengths, from 1,000 to 32,000, using blockwise causal attention during inference to enhance the model's ability to generalize sequence lengths. We compared how standard transformers and LongNet scaled with context length. Our method of estimating the computational effort was to calculate the total number of floating point operations, flops, involved in matrix multiplication. We found that both types of models benefit from training with larger context lengths. However, LongNet was able to scale up context length more efficiently, achieving lower test loss with less computational effort. This result emphasizes the advantage of training with longer input sequences over using extrapolation methods. In summary, Our experiments demonstrated that LongNet provides a more efficient method for increasing the context length in language models, primarily because LongNet is more effective at learning long-range dependencies. Section Summary. In this section, the authors compare LongNet with vanilla transformer and sparse transformers, scaling the sequence length from 2K to 32K. LongNet consistently outperforms the baseline models, demonstrating its effectiveness in language modeling. The authors also investigate the performance of language models when the context length is scaled up during training and find that LongNet can scale up the context length more efficiently, achieving a lower test loss with a smaller amount of computing. This highlights the advantage of longer training input over extrapolation and shows that LongNet is a more efficient way to scale up the context length in language models. Section 4.4 Scaling up model size. 4.4 Amplifying model capacity. An interesting characteristic of extensive language models is how their performance relates to the computational resources used to train them. This relationship typically follows a power law. To confirm whether this pattern also holds true for our LongNet model, we trained several versions of it, varying in size from 125 million to 2.7 billion parameters. Our most parameter-heavy model, with 2.7 billion parameters, was trained on 300 billion tokens. Meanwhile, the other models were trained with around 40 billion tokens each. We observed the relationship between the computational power used and the model's performance, as measured by perplexity on the same test set. Here, we approximated the computational power used by counting the total number of floating point operations, or flops, performed during matrix multiplication in the training process. The findings confirmed that the LongNet model does follow the power law when it comes to scaling with computational resources. This important discovery means that you don't necessarily need to use a dense transformer architecture to scale up language models. It shows that LongNet not only scales well but also operates efficiently. 4.5 Extensive contextual prompting. Prompting is a valuable tool for language models, offering extra information and guidance. We were interested in determining if LongNet could improve its performance by leveraging a larger context window for prompting. To test this, we designed an experiment where we set aside part of the input as the prompt and then assessed the model's perplexity in generating the remaining part. We gradually increased the length of the prompt from 2,000 to 32,000 tokens. To keep the comparison fair, we kept the size of the remaining part constant, while increasing the length of the prompts up to the maximum capacity of the models. Our results showed a consistent trend. As the context window, prompt length, increased, the test loss for LongNet decreased correspondingly. This outcome indicates that LongNet is indeed capable of effectively using a larger context to enhance the performance of the language model. Section Summary. In the section, Scaling Up Model Size, the authors train models of different sizes and find that LongNet follows a power law scaling with compute, indicating that dense transformers are not necessary for scaling language models. In the section, Long Context Prompting, experiments show that LongNet benefits from longer context windows, as the test loss decreases when the context window grows, demonstrating the model's ability to fully leverage long context to improve language modeling.